Hi, I'm Arthur. This is my Lab 2 motion of a falling object lab report. The experiment. We will observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. We will then construct an observed position versus time graph through the use of Tracker to analyze the video. Then, we will construct a predicted position versus time graph by making two separate computational models that apply this concept of Newton's second law, with one having just the force of gravity and one with both the force of gravity and the drag force, respectively. Finally, we will compare the observed and predicted position versus time graphs. The subject of my experiment. My experiment examines the position versus time function of a ball being dropped from a meter height. The ball seems to speed up as it falls, though it cannot be determined for certain if the ball is subject to air resistance without further data analysis. It falls towards the floor, so the force of gravity is likely to be present. This is the video. So in Tracker, I analyzed when the ball is dropped from the hand to when it hits the floor, so before it bounces. So Newton's second law and the turbulent drag force. So V final equals V initial plus F net divided by mass times delta T. That's the velocity update derived from Newton's second law. I have R final equals R initial plus V average times delta T. That's the position update derived from Newton's second law. And for turbulent drag force, we have the drag force equals the drag constant times V squared times V hat, where V hat designates the direction of the drag force. So this is the tracker data. It starts at 1 meter and then ends up at 0 meters. And then it starts at a time of 0 seconds and ends at a time of 0.517 seconds. Applying Newton's second law, just gravity. My computational model code for just gravity applies Newton's second law in updating the position and the velocity. The time interval was chosen based on the tracker data for consistency, so 0.517 seconds. The velocity update uses the formula V final equals V initial plus F net divided by mass times delta T, shown right here to find ball.vel. Position update uses R final equals R initial plus V average times delta T, that's shown by ball.position. So applying Newton's second law, gravity with drag force. This one's a little bit more complicated. My computational model code for gravity with drag force applies Newton's second law and I'm updating the position and the velocity. The drag force is calculated by creating a variable that stores the magnitude of the vector. So that's here. I used vel underscore mag, standing for velocity magnitude. And then the drag constant, which is b, is found through trial and error to make it match the observed start and end data points from the tracker data as closely as possible. So my value of negative 0.858 is found from plugging it in, running the code, and then trying to make it start at 1 meter and then end at 0 meters. The time interval was also chosen based on the tracker data for consistency, 0.517 seconds. And then the drag force is represented by this equation. Force of drag force is represented by negative b times v squared times v hat, and you have to put the code equivalent after finding the v value through trial and error. So that's right here, expressed in code. So the glow script model results. So the one on the left is just gravity, and the one on the right has the gravity and the drag force. You can see this is the drag force, and this is gravity. Alright, so the tracker and model comparison. The model with just gravity ends up way below. Like, it's all the way down here. And then the model with gravity and drag force ends up far closer to the observed data. So it starts at 1 and then ends basically at 0, like right on top of the observed one. I just wanted to put this here. It's pretty difficult getting all the data points from GlowScript rather than just choosing a select few, because the text box scroll is really sensitive on GlowScript. You try to highlight a specific data point and then paste it in here, and then it highlights the entire GlowScript text box. Just a little tangent I wanted to talk about. Okay, so the GlowScript model comparisons. What does it mean? The model with gravity and drag force predicts a terminal velocity as the velocity approaches a value around negative 3 meters per second. So you can see it basically bottoms out around here. The model with just gravity does not predict the terminal velocity, as the velocity has a linear slope, so it's just a straight line, as the force of gravity is constant and is the only force depicted by this model. So this one will just keep going down forever and ever, because there's nothing else slowing the gravity down, I guess. Alright, so what if we were asked to imagine that the object was initially thrown downwards, with the initial terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? Alright, so For this scenario, the terminal velocity in this case would be the same, though it would reach it earlier. The model with gravity and drag force approached around negative 3 meters per second as a result of the formula, Fd equals negative b times v squared times v hat, being balanced against the gravitational force, where the difference in magnitude between two forces becomes more and more negligible, as in, this one slowly approaches the gravitational force in the opposite direction, so they cancel out. Thank you for listening to my lab report.